Hi, I am Sabrina binti Hairo Azhar from Group 12. I am going to explain in detail about the code executed to generate the binary FSK modulation and demodulation with AWGN channel. This code is divided into four main parts, which is the binary data in digital form, the binary FSK modulation, the AWGN channel, and the binary FSK modulation. However, before we start, the first thing we need to do is to declare the input data here, which is 0110010. Now, let's move to the first main part, which is the binary data in digital form. In this part, there are two subparts, which is the first one is to convert matrix digit into digital input to represent the input data as digital signal. As for the second subpart is to plot the graph of the digital input signal. Now let's move on to binary FSK modulation part. In this part, it is divided into three subparts. Okay, for the first subpart, this is to declare the carrier frequency for high and low data input, which is F1 and F2 respectively. For the second subpart is to compare the input data, which is if 1, insert carrier frequency for high into matrix modulation and vice versa. And for the third subpart is to plot the modulation signal. Now, let's move to the AWGN channel. AWGN channel add the white Gaussian noise that imitates the surrounding noise. The existence of the noise allows the data to transmit wirelessly. As we can see, AWGN channel is plotted on the same graph as the modulated signal because this noise is added into the modulated data. That is why it is plotted on the same graph as the modulated signal. The most important part in AWGN channel is SNR, the SNR code, where it will determine the noise insert into the modulated signal. If the SNR set is too low, it will affect not only the modulated signal but also the demodulated signal. Last but not least, the binary FSK demodulation. This part is divided into four subparts. The first subpart is where the modulated signal recombine with carrier frequency through convolution and integration. The second subpart is where the result is then compared with half of the carrier signal amplitude. The third subpart is to convert matrix digit into digital data to represent the demodulated data as digital signal. And lastly, this is where to plot the demodulated data. This figure shows the output spectrum of the message signal, the binary FSK modulated signal, and the demodulated signal. And as you can see, the input and the demodulated signal is both in a digital signal. And as for the modulated signal, as you can see, there is no noise exists in the modulation signal as we set the SNR to high, which is 50. If we set the SNR to a very low value, which is for example -10, it will cause a distortion on the modulated signal and the demodulated signal. This proves that FSK is resistive towards noise when SNR is set as high. That's all from me. Thank you.
For BPSK modulation part, we have simulate the circuit in Simulink in order to get the BPSK modulation technique. First, We use a Bernoulli binary generator as our input. This because this block can generate a random binary number by using a Bernoulli distribution. If we see at this first row of scope, this waveform show a input of the circuit in binary, and this waveform will change for each time the circuit will simulate. However, this input data is in complex form, which have a real part and imaginary part that can see in this figure. Then, this input data have been sent to the BPSK modulator baseband. This block modulate the signal by using the BPSK technique. If we see at the second row of the scope, we will see that the input data have been modulated. This because its waveform have phase condition from the input data. In binary message, the binary 0 represent for condition which is no phase, and binary 1 represent 100 degree phase. So we know the data has been modulated. Then the data will be sent to the transceiver. This transceiver is contain a transmitter and receiver part. In order to get the wireless transceiver, we use AWGN channel because it can mimic the surrounding noise. By control the SNR in EB over NO, we can control the noise. For this simulation, we use default setting which is 10 dB. From the third row of the scope, we know the data has been distorted with the noise. Then this data will be sent. To the BPSK demodulator baseband, and this block as a function to demodulate a signal by using BPSK technique. If we see at the fourth row of the scope, we can see the output data is exactly same with the input data, and this can be proved by using the error rate calculation, which is as a function to compare the transmitter input data to receiver input data. This display have three data which are: first row is width of error (VER), second row for total error, and third row for total bit. So we know the data is distorted, but the data signal will not get buried under the noise in transceiver process. Then we also change the SNR of EB over NO value to -10. Based on the observation, we know the output data have some error because this display show the total of error for this process. This because the data signal is get buried under the noise when the transceiver part. Then we also change the SNR value to 50 dB. Then based on the observation, we know the output data is exactly same with the inputs data because the input data does not get buried under the noise, and the signal does not get distorted with a noise. For the result of this simulation, we can conclude that with a high channel noise, the signal get buried under the noise, and with a less channel noise, the signal does not get buried under the noise. That's all. Thank you.